Learn how to engineer smarter and faster, all while outbidding your competition by using the automated network sizing module to drastically improve time efficiency and put more money in your pocket. With it, not only can you design an entire pipe network around specified design requirements, you will find the size that minimizes costs. That's right, no more manual iterations and no more oversizing and wasting money. So I'm going to show you how easy it is. We're going to find the right pipe diameters to meet my requirements and to minimize life cycle costs. Here's an example of a cooling water loop that was designed to meet certain flow requirements through each heat exchanger, and that is 2,000 gallons per minute. All of these pipes were then sized according to traditional engineering practices. So for example, this pipe leading into the first heat exchanger was sized to be 14 inches for a nominal size, and we're going to test that against the numerical methods used in ANS. So the first thing is we have to make sure that the module is activated. Once you see that it is activated, you're going to find this new window tab pop up called sizing, and you guessed it, that's where we're going to work our magic. And remember, we're not just sizing for the single pipe, we are sizing for the entire network coupled together. I have just pulled out this pipe as an example for you to focus on. So again, it was originally sized to be 14 inches. So the first step is to go to the sizing tab here. And you will notice the sizing navigation panel down below that'll walk you step by step on how to do this. So first we have to choose our sizing objective. I want to minimize monetary costs, and not just my initial costs, but my recurring costs such as energy as well. And if you have any sort of finance background, you understand to do this, we need a system lifetime. So I've chosen 5 years and a company interest rate or hurdle rate defined by your company, usually around 10%, and an inflation rate. And I've chosen to use the national average of 12 cents per kilowatt hour for my energy cost information. However, you can put in your own data if you have that available, but this will suffice for now. Then we go down to our size and cost assignments. And once in here, we're going to choose our common size groups for our pipes and our pumps. So for pipes, this is intuitive because you know in and out of a heat exchanger or the suction and discharge side of a pump ought to be sized to be the same. Well, the same is true for pumps. If one of these pumps supplies less power than the other, well, we want to size according to the maximum power required because these pumps are going to be the same size pumps, most likely. So you see that here, we're going to size them all the same according to the same databases. Now, candidate sets is the next tab. What we have here is the range of pipe sizes that I want the software to run through. So I've chosen 1 inch all the way through 36 inches just because I want to have a wide range. I want to see what the software will tell me is the best size. Once I do that, I go to design requirements. This is where the rubber meets the road. This is going to be unique to your system, and this is how the software will decide what is the appropriate size, because you have to define, you have to put a fence around it. So here we've got a maximum velocity, a minimum pressure. Well, I'm going to add a minimum flow rate. Not that we need it because we actually have flow control valves. If you remember, we actually needed 2,000 gallons per minute, but I just want to show you how easy it is to add these requirements. Going through the cooler piping, there we go. Okay, through the pump, we have a minimum net positive suction head margin to avoid cavitation. On the control valve, I've got a minimum pressure drop to ensure good control. And once in the cost database section, all we have to do is make sure that our engineering database and our cost database line up. So here we've chosen the correct one for our pipes. For our pumps, we've also chosen the correct one, and we're good to go. The last step is to choose the sizing method. I have chosen discrete sizing because I want to only use commercially available sizes. We run the model, and in a matter of seconds, we've run through hundreds of designs to figure out the best one to meet our design requirements. So let's check out the output. Once here, you will see that our original system cost $1.79 million. We have got that down to $1.72 million. That's a cost savings of $70,000 to put in your pocket just by taking a few seconds and running the simple software. So we go down to find what sizes the software came up with. So you can see here, actually the software came up with a pipe size that is larger for one of the pipes, and that's because that is to decrease our energy consumption. So as the pipe diameter increases, we use less power, and over 5 years that adds up, so we've actually increased the size of one of our pipes. However, we've decreased the size of others. So that 14-inch pipe I told you to pay attention at the beginning of the video was actually sized to be too large. We can get away with a 10-inch pipe and meet the same requirements and drop our costs. That's the power of ANS. Not only have we designed an entire network around design requirements, we have found a design that minimizes costs. Again, that is the power of ANS. So I hope I've piqued your interest in this software. Please contact us directly or your local channel partner to find out more information. I wish you a great day and happy engineering. Cheers.